So welcome to the last lecture of the semester. Actually, you're all giving the last lecture of the semester, if you recall. That's next Thursday at the poster session. We'll all be in here, and you can all give 1-minute summaries of your posters before we walk out to drink coffee and actually look at the posters. So today, I'm happy to welcome Christine Persson, who's a research scientist at Lawrence Berkeley National Lab in the chemistry division, who's going to tell us about how high-performance computing can build better materials.
Thank you, Jim. I'm very happy to be here. It's exciting to give a class in a topic that I wasn't a student of, and I'm only learning about it, computing science. Like Jim said, I'm a material scientist. I started out as a physicist. I use the Schrödinger equation and computations to calculate properties of materials and try to accelerate the development of better materials for a better future. So the outline of today's lecture, and I'm mixing a lot of things in here. I'm hoping to excite you a bit of what we can do with computations and high-performance computations. The motivation is material science to the rescue for a sustainable energy future. Then the Schrödinger equation that we use to calculate these properties, I'm going to tell you about an implementation of it that is very usable, called the density functional theory, so a bit of a crash course on that one. And then I'm going to be talking about how we actually compute things on high-performance computing clusters. So our methodology is not an exascale poster child. So we're trying to fit our computations into the center policies and the concurrencies that exist at those places. So I'll tell you a bit about those problems, and then assume that we solve those problems, does this work? And I'll tell you about some of the projects we've done in the past. And at the end, I'll talk about the materials genome, which is sort of the vision of what we're going to do with this long term. And if we get a lot of computing and a lot of people excited, I think we can get there. So materials. I don't know if anyone here has read anything about material science or are interested in cars, electric cars, photovoltaics. I see some nods. Good. I'll tell you a little bit about it. So fuel cells. Anyone know what a fuel cell is and how it works? Fuzzy idea, right? Okay, so it's a very clever, beautiful concept. It's about taking hydrogen and hydrogen and oxygen, so hydrogen from some source and oxygen from the air, and turning it into water using a catalyst. And you get energy from that. And you have a clean waste product, water. It's a great idea. Unfortunately, people have been working for 20 years on trying to make this work in the way that it's cost efficient and we can run the cars for a long time, for example. The two problems that are hindering this technology from taking off are materials problems. There's the problem of hydrogen storage. We don't have a material that stores, that you can insert hydrogen into and take it out of that material at a low energy cost. That's what you need in order to store it, right? You have to bring the hydrogen to your car in some way. We don't have a catalyst that is inexpensive and that lasts. The best catalyst for this problem is platinum. So in order to make and super expensive, right? So in order to make the best use out of platinum, people make really, really small nanoparticles with huge amounts of surface area because that's where the reactions takes place in a catalyst. These small particles, and I'm going to use the mouse to point. These small particles of platinum, they dissolve in the very acid electrolyte. So this is a Probet diagram. Bear with me, it's the potential. So around here is where the reaction in a fuel cell takes place. Now my mouse disappeared. Okay, let's try this instead. Here we go. Here is where a fuel cell lives, where it sort of cycles. And this is where noble platinum dissolves. Here we go. And the small platinum. So these tiny particles that we make tiny because of the large surface area, they dissolve in the electrolyte, they coalesce on bigger particles, and you lose performance. So these fuel cells don't last more than a couple of months. And then you have to put more platinum into them, small nanoparticles. So very inefficient, doesn't work very well. Two materials problems that are hindering this technology from taking off. Another one is photovoltaics. So you think about photovoltaics, you probably think silicon, high-grade silicon, cadmium telluride, stuff like that, and you've heard about things, yes, they're very toxic, but it seems the people who try to make that work, they make a good case for it. Silicon is one of the most used, silicon wafers. This is a plot that tells you how much, see, oops, that doesn't really work well, how much the cost of a photovoltaic, and this is from domestic sources and foreign sources, how much of a photovoltaic comes from making the actual panel, not just the material in itself. So all the stuff that goes in there, there's a lot of other things in there, transparent conductors, there's like lots of materials and gadgets and things to make it work. So most of the cost is actually making the panel. It's not in the material itself. So what's the best way of getting more kilowatt hours per dollar? It's not going after all these different things. It's making your active material more efficient, more bang for your buck. So assuming that all the other costs are fixed. You can work on those too, but that's sort of incremental, one at a time. But putting more energy density or more efficiency, turning solar energy into electricity more efficient, that will sort of scale the cost per kilowatt hour directly. So that's a great way of doing it. So again, a materials problem. Have you guys seen Back to the Future? I realize this is a very old movie. When I put this up, and I got it, I thought this was hilarious, right? This is from my time period. Doc and Marty in 1989 or whatever it was, 1986, takes a DeLorean to the future. And believe it or not, in 2012, they are making electric DeLoreans. And I just remember Doc saying, no, this sucker is electrical, but I need a nuclear reaction to generate the 1.2 gigawatt to get it going, right? So we don't exactly need a 1.2 gigawatt to get our electric cars moving today, but it is an energy problem. We're putting lithium-ion batteries into these cars, and we can't make them last as long. We can't make the cars go as long as we would like to. The Nissan Leaf goes about, they claim 100 miles. We can get about 70 out of it, especially if it's warm outside and we need to get the AC going as well at the same time. Again, most of the cost of a lithium-ion battery goes into the cell. It's not the active material itself. There's a huge amount of engineering and stuff going on in it. And some of the things I show here is like, there is the, there's the cover, the current collector, there's a separator, there's the electrolyte, a lot of different things that goes into a battery that's not the active material. If we can have more energy density per all these cost issues, we can get, again, more bang for our buck. Has anyone here driven a Nissan Leaf or looked into it? No. Tesla? No, of course not. They're so expensive. Well, Prius it's true, but the battery there is very small. But if you think a real electric car, the battery basically sits underneath the whole car, underneath the seats. It's like a giant spider underneath the seats because it's so big, they don't know where to put it. They can't put it in the trunk anymore. They have to put it underneath the seats. So it's this like I don't know, parasite that sits underneath the car. And that's because they don't know where to put it. And they've made it as big as they possibly can. The volumetric energy density of these things are killing them. They can't put more stuff into them. It's not the weight, it's the volume. So having an active material, a cathode material that has more energy density per volume or per cost would greatly reduce or increase the viability of these things. So again, a materials problem. Politics, strategy, countries' economics. Does anyone remember this? This was just last year, so not the 80s, thank God, anymore. In 2010, Japanese police arrested a Chinese boat captain who was infringing on their water somewhere. They didn't release him, but 2 weeks later, China blocks all shipments of rare earth metals to Japan for one boat captain. And China is the one supplier in the world of rare earths. We can't get them for anywhere else. We can get them somewhere else, but it's dirty mining. We don't want to do it anymore in the US. We're actually starting up a mine here in California. Molycorp is starting up a mine because we don't want to be dependent on China anymore. But we closed it 5 years ago. We now have to open up again because of this issue. Some of the rare earth metals have increased by a factor of 100 in the last couple of years just because China wants to keep all the rare earths. And they're critical materials in the sense that they're unbelievably important in some applications. So for electric motors, for example, they're permanent magnets. And you use them in electric motors that, again, are used in electric cars or windmills, stuff like that. What happens? 2 days later, Japan releases the captain. But Japan is not very happy about this. So they started investing in induction motors that don't use these permanent magnets because they hate being dependent on any other source, and especially China. And last year, Toyota announced that they are now readying motors that don't use rare earths. That's one approach to materials problems. Try to find an engineering solution that works around it. Another solution is try to come up with a material that you have domestic sources for, or try to mine them again, like we're trying to do here in the US. Coming up with new materials, and then now we're getting closer to my area and what I'm doing, is unfortunately a very long, time-consuming business. Traditionally, it takes about 15 to 18 years to launch a new material, and that's from the time it works in the lab to being commercially successful. And works in the lab, I mean, that's a real material that works, right? So what is the problem with this? According to Eager, who made the study in 1995, and this is still true, somebody actually remade the study just a year ago to be sure that's still true. It's because we don't have enough information about the materials when we select them. So think about an experimentalist. He's trying to come up with a better lithium-ion cathode. He's sitting in his lab. He's very happy if he can come up with something that has a little bit better energy density than what is currently out there. And he tests it under normal temperature conditions. He makes about 1 gram of this material, and he cycles it about 50 to 100 cycles. And if that's good, he's good to go. He files a patent. He sends it off somewhere. Somebody licenses it. And then they try to scale it up. They test it under different temperature conditions. They test it in a real application, in a real environment. And suddenly they find out everything that's wrong with that material. And they have to engineer around it, and they have to come up with solutions, and that's what takes time. So if the people who make the material, come up with the materials in the first place, had more comprehensive information about, how durable it is, if it has elastic problems under different strains, if it's temperature sensitive, if it can actually be made in large batches and not on the gram scale, if you can scale it up, then we could shrink this time scale. So one of the issues is having more information about the materials up front so you make a better choice. You may not have gone for exactly that material that the investigator went for. He might have gone for something else with less energy density, but had better properties overall. He made a more informed choice up front. And that's where computations come in, because we can calculate a lot of properties of materials using quantum mechanics and a lot of other methods, but this is our main workhorse. And to turn those into engineering properties, unfortunately, there is no quantum operator for a better battery, but that's where the scientist comes in. So we basically take all the stuff that comes out of the Schrödinger equation. By being smart about what's relevant and how to interpret it, we turn that into things that are important for people. Like if you're going to come up with a better battery, it's voltage, capacity, energy density, temperature sensitivity, release of oxygen for safety, a lot of these things. And all these things can actually be calculated using the Schrödinger equation, but you have to know how to interpret it. So that was the first sort of motivation. So now we know what we want to do. We want to calculate properties of materials so we can make a better selection about them up front and work with experimentalists so that they can come up with better materials to solve these engineering issues and our future energy sustainability. Ab initio calculations, that's what I do. And it basically means from the beginning. It means that we take the atomic numbers, the elements themselves, and our knowledge about how many electrons and how many neutrons, or how many electrons and stuff they have in there. And we use the Schrödinger equation from the beginning. No adjustable parameters. I'm not going to say no approximations because we're going to come to that soon. But there's no experimental input. We don't take I know what the elastic constant of this material, I'm going to fit some potential to it, and I'm going to calculate properties. We don't do that much. We do a little bit of it, but we actually calculate everything from the beginning, ab initio. We also call it first principles. And we try to predict physical and chemical properties of the systems that we're interested in.
So, question.
Yes.
So you might not start with a crystal layout and then ask what happens?
We assume where the atoms go.
Okay.
Or we start with a good guess. But we can let them relax.
Okay.
In different, so that includes solving the Schrödinger equation with finding the optimal position for the atoms and the electrons. And positions on electrons, that's a bit fuzzy, right? They exist in a wave function that is, so there is no way of pinpointing them. The Schrödinger equation that we solve, so different applications require different approximations. We solve it steady state because we're interested in ground state properties of materials most of the time, which means we have no time dependence. So it's an eigenvalue problem. The Hamiltonian times the wave function is the energy times the wave function. And the Hamiltonian includes the kinetic energy of the system and the potential energy of the system, just like you're used to. So this is a crash course, right? I'm going to try to go through it as top level as possible. When you divide this Hamiltonian, you look at the nuclei and the electrons. And you have the kinetic energy for the electrons here, and your kinetic energy for the nucleus, and the potential energy for the nucleus, and the interaction between the nuclei and the electrons, and the interaction between the electrons and the electrons. Very simple. You just divide it up like that. The first good news is that we can separate out the nucleus part, because the nucleus lives on a completely different time scale than the electrons. Whatever you put the nucleus, the electrons are going to swish, go over there and be their ground state right away. So we separate that out, and we solve that as a separate partial differential equation. The electrons is the problem, because they interact, and there's so many of them. And this is a true many-body problem. The number of computations scales as exponential with the power of n, and n is the number of electrons. We can solve, using supercomputers, a true many-body Schrödinger equation with up to 4 to 5 electrons. That's nitrogen. It's not going to get us very far in terms of materials design. And materials contain of the order of 10 to the 26 electrons. So this is intractable. There's no way we can throw supercomputers at this and solve it exactly. So we have to come up with clever approximations. And that's where density functional theory comes in. It's just a clever approximation. So a bunch of people, maybe 20 years ago, called Cohn and Sham, they come up with a way of, first of all, we're going to cast this into a density problem and not a wave function problem, because the density is easier. It doesn't have as many variables as a wave function. Second of all, we're going to take everything that we know, that we can calculate exactly, and put that into one bucket, and take all the tricky many-body problems that has to do with all the electrons interacting with each other, and put that into one bucket. And that's what we call, this part here, interaction between the electrons. These part here, and that contains the kinetic energy is both the electrons and the nuclei. And we're going to assume that the electrons then, they live in a sort of a bath of interactions from the other electrons. That's an approximation. And how we calculate that bath of interactions, there are different ways of approximating that. And I don't know if anyone has ever done this. You're going to hear that there's a variety of these approximations out there. They're called LDA, GGA, GGA plus U, Hartree-Fock, whatever. There's lots of different ways of doing this. But the essential idea is that you cast the many-body problem into a one-body problem, so that this one electron lives in a mean field interaction with the rest of the electrons. So it's like I'm sitting here, the density is a function of me at this one place, but I'm interacting with all of you, but on a mean field sort of approach. I'm not seeing individual interactions with you. I'm seeing the whole thing. That's the idea. When people came up with this, so Walter Cohn got a Nobel Prize for this idea after a while, because this has turned into quite, I would say, a significant breakthrough in terms of solving the Schrödinger equation. Without this, we wouldn't be able to do much more than nitrogen and a few other systems. It's surprising how well it works, because one of the most common approximations, the LDA, is literally just looking at a homogeneous electron gas, for which we can solve it exactly, and calculating these many-body effects from a homogeneous electron gas, and assuming that everything out there that are far from homogeneous have many-body interactions that are similar to that homogeneous electron gas, which is weird, right? Anyway, using this approximation, we can calculate a lot of different materials properties, and this is just a very small slice of things that I've been involved in. This is phase diagrams up here. This is a quaternary phase diagram between lithium, iron, oxygen, and phosphorus. And we can look at all the different stable phases. This is the convex hull for those guys of you that are like mathematicians. We just take all the energies of these different phases and we compare them to each other. There's the diffusivity of lithium. That's the second graph. There, oops. This one in graphite, that is important for lithium-ion batteries. This is voltages for different cathode materials compared to experiments, and as you can see, we do pretty well. So there are no fettered parameters in here, but we can calculate these voltages really well. Then there was the dissolution of the platinum particle. These are particle morphologies. We can calculate that from surface energies. This is how different materials release oxygen at different temperatures, which is important for safety. That's one of the failure mechanisms for lithium-ion batteries, when the cathode, which is highly oxidized, releases oxygen to the electrolyte, which burns, and then boom, goes the battery. You've seen that in laptops, right? It's on YouTube. And it's very frightening. We can calculate reaction energies, and the last plot over there is band gaps as a function of different elements. So a lot of cool properties can be calculated. And the good news about computations, again, we can scale them, hopefully. If we have one material and one computer, we can calculate, a lot of different properties for that material. If we have two computers, we can do two materials and so on. This is very simplistic. I'll try to get into that a little bit more. So this is where we're sort of going into the computations. How do we actually scale the computations using our methodology, which is the density functional theory to get materials properties? So DFT codes, and this is something that when I was a grad student, I actually parallelized the DFT code. It was very badly done. I couldn't scale it to more than, 5 CPUs or something, but I was happy to do it because it's super easy. You just Fourier transform your Schrodinger equation, you spit out the calculation on a number of different k-points grids in space, and all those points are independent. So it's really easy. You can do it. But you have to then, once you've gotten the energy on every k-point on your grid, you have to put them all together, and you have to get the total energy, and you have to do that a lot of times. There's a lot of communication going on between every time you do is spit it out on all these k-points, you have to bring it back, calculate the total energy, put it back out again, keep doing that. It kills the scalability of your problem. And there are much more clever ways of parallelizing DFT codes, density functional codes, but unfortunately, no one seems to be able to get around that communication problem. So the best scalability I've seen is about 30 to 40 nodes. After that, they all die. They go down. So if you put more nodes on the problem, you're going to get worse performance. And if you have any questions, yes?
So is the particular bottleneck the Fourier transform then?
No, I think it's from my perspective, it was the communication. It was bringing all that back. Okay. The Fourier transform itself, I think that's very fast, right? So what we typically do, we put one material per node, which has 8 cores or something. So that's within what it scales, and that's really nice. And you have all the communication within one node. That then you run into problems depending on how many materials you actually want to run. If you have your own cluster, you're fine. It's because it tends to be that all of these calculations take a very different amount of time. If I'm going to run BCC iron, very simple, ground state of iron, it takes milliseconds. It didn't used to take milliseconds when I started in the field 15, 20 years ago. It took a few hours, but today it takes milliseconds. If you're going to run a very large supercell with 200 atoms, and it has 4 elements, and one of them is bismuth, which is super heavy, lots of electrons, it could take weeks to do it on one node. So you're running into a problem that if you're going to calculate a lot of these things, and you can to some extent predict how long it's going to take, but not completely. And this is a chart that David Skinner, that works with me for NERSC, made a few weeks ago. And it's actually from our project where we calculated 20,000 materials. You can see how hard it is to predict exactly how long it takes. So we tend to think in terms of electrons. In terms of electrons, that's something that would scale. And in terms of atoms, and the color scheme here is how long it takes. Red is weeks, green is days, blue is hours, and down here are a few small dots, magenta, for minutes. So you think, well, lots of electrons that should take a long time, but you can also see that a small number of electrons down here, there are some red dots there too. And same thing here, lots of atoms, yes, that definitely correlates with red, but there are some red down here and some green down here. So obviously, there are systems that are really hard to calculate, even though they're small, and there are big systems that are easy, even though they have a lot of electrons and atoms. So it's not that easy to predict, and it has to do with symmetry, how much you relax the atoms, like Jim was asking before. They move around, you relax. It depends on how good of a starting guess do you have, or where the atoms and the electrons like to be.
So to use terminology from an earlier lecture, this is a load balancing problem? Is that what you mean?
Probably, right? Load balancing to some degree. Is that the right terminology?
Within a calculation or amongst all?
Amongst all of them.
Yeah, depending on A lot of people don't think of load balance over days or weeks, but yeah.
Okay.
So when we deal with this, we try to bin so that we have the ones that we think are going to be fast in one bin and the one we think are going to be long, but we still have a lot of discrepancy within these predictions. This is also some graphs from NERSC where one of the DFT codes that is very commonly used called VASP is one of the biggest users of NERSC actually. And you can see that this is the time versus the run number, and this is just whatever was run at that time. You can see it varies tremendously. They put in one computation, it takes nothing, and then they take the next one takes a really long time. Yes?
That's a log scale?
Yes.
Okay.
I believe so. Yes, it is.
On the one.
Yeah.
Yes, right.
Yeah. So let's say you're asking for 500 nodes for 500 jobs. That's good if they all take the same time. But if half of them finish in 2 seconds and the rest of them go for 2 weeks, you've been very inefficient. If all of them actually don't finish in the time you asked for, then you have to restart your problem, which takes time as well. It's a nightmare, to be honest. And one of my postdocs is willing to, he's tearing his hair, and he has very long hair. It's down to here. He's a true Berkeley guy. So we're dealing with this is a headache. You have to be smart in how you bin them. You have to manage them in the sense that when they die, when they're killed, when they don't finish, you have to restart them. You have to take care of them, put them back in, and you have to be smart about that. You also have to deal with the policies of wherever you're running. And we'll get a little bit into that, and I'll tell you some examples of some computing systems that are, or centers that are more amenable to our problem, and some that are very, very uncooperative. So basically, this kind of issue requires a scheduler, some kind of workflow environment where you, as a user, you don't just submit your 200 jobs to the queue because the queue might have issues with that too, and let them figure it out when they want. You actually have to figure out, I'm going to put a work manager that manages my jobs on top of the supercomputing queue and submit them in a certain way and take care of them and put them back in. And this is very different from the typical large-scale jobs that people are asking for. The exascale jobs are either ginormous simulations that all talk to each other for one data point or one day of a climate issue somewhere or one cloud formation or whatever it is, or completely independent jobs like Monte Carlo, where you can spit out, single simulations on 200,000 cores and you're fine because it scales over how many you want. They don't talk to each other. So you have to figure out how many cores are you actually going to use. What is the best ones for your problem? Is it 30 to 40 or times whatever, 30 to 40 nodes, or is it more? So whatever fits your problems best. And policy at your computing center. For how long can you run? NERSC allows 2 weeks. If I have my own computing cluster, I can let it run for whatever, and that's what people in my environment typically do. They buy a large cluster on their own, put it in their basement, have a poor grad student that manages it and tears his or her hair because it's a major pain to be dealing with the cluster, right? But that's great because you can just run your jobs for how long you want. You don't have to deal with the restarting. Yes?
Could you say again what synchronization is required? You have to wait for all the jobs to finish, collect their data together, make some decisions, and then start them up again?
Yes, so you have to...
So they're not all independent. They do have to communicate.
No, they're actually independent, but we tend to batch them because of this issue that, because of queuing issues, because of concurrency issues, basically trying to work your problem into a high-performance computing center as best as possible. I'll try to describe it. So again, on a local resource, you do what you want, right? You submit your thing to your own cluster, you let it run. If it takes 10 seconds, you're fine. You can put 200 things in the queue and you're happy. They'll just run whenever they run, right? But if you put them at NERSC or somewhere else, a high-performance computing center, they only allow X number of jobs in the queue, for example. So if you put 200 things in, they're just going to kick you back, or they're going to wait for months to get the last things going. So that you don't want to do. On a shared resource, so you have to work around that. You also want to make sure that you don't ask for, you want to make the most out of that system. So if you ask for 200 jobs, that's going to take 2 weeks, you may wait a long time in the queue because that's the maximum they allow. If you ask for 50 that takes 2 weeks, you get in faster. So these are the things you have to think about. This is actually a plot from NERSC that, again, David provided. And this is the number of cores at any given time as a function of time of that job running. And as you can see, all these different colors here are different jobs running at that particular time. And this is how long they ran on the x-axis, and on the y-axis is how many cores they asked for. So you can see what a huge job it is scheduling all these different computations into one supercomputing center or one machine. I don't know, is this Hopper, David, or?
This is actually an IBM machine.
Oh, OK. And one of the things they care a lot about is efficiency. They want to fill their cluster as much as possible for any given time length. And because that's one of the metrics that is easiest, right? How much did we utilize our cluster? And you see that single spike over there? This one here? That's somebody who asked for a ton of cores for a relatively short time, but still. They had to make sure to terminate all of those other jobs and make sure that they all stopped so that they can accommodate that one single job. So if you submit that request, you're going to have to wait a long time because they have to finish off all of those small jobs and then make the whole cluster available for you. So you can see that if you want to run as much as possible in a given time frame, you might not want to ask for that unless you really need it. If that's the only way you can solve your problem, you have to do it that way. Don't get mad, get even. Yeah, that's a good one because I see that a lot, again, with my poor postdoc with his long hair. He's trying to get all, he's very passionate about what we're doing. We're running a lot of different materials and different properties. And we got allocated 10 to 20 million CPU hours the last two years, which is great. We're very, very happy about it. So he would like to run, he would like to start in January and just run forever, but that's not going to work. That's not how the queuing system works, and that's not how a high-performance computing center works. You have to fit within that model. So what he's doing is that he makes sure that these queuing policies, he puts enough, he puts the minimum amount or the maximum amount of job requests in, but then he batches a lot of different jobs into one script. And then he puts all those out. That's how you write it. That makes sense? He submits one script that launches a lot of small jobs that are independent. It's one way of doing it. I love this graph, by the way. I think it's really cool. And I can just see that this is a computing science problem in itself, how to make this in the most efficient way. And I can also see that different high-performance computing centers solve this in different ways. So for example, I'm part of a large collaboration that's trying to propose a battery hub for DOE. And one of the supercomputers that they're trying to get into the proposal is Blue Gene. Blue Gene is unbelievably uncooperative when it comes to this core policy. It doesn't admit any software that doesn't scale to 1,000 nodes on that machine. So I'm out, right? Density functional codes are out. Not going to be running any of those. It's not going to happen. So, but NERSC is pretty nice. They have realized that some science does not fit into the model of everything is unbelievably scalable. But it is, you can sort of see that it makes your life a lot easier if you can just assume that model, because then you can design your architecture for the kind of computing problems that are fit into one model. If you have to accommodate a lot of different models, both very scalable problems and both things that works on a small number of nodes, you have to have a very flexible system, and you're going to have a lot more downtime.
So just to be clear, each one of your jobs uses a constant number of cores, and they have which is a relatively small number, but they have this tremendous range of run times. Yes. So would you be interested in being able to scale up to larger numbers? I mean, once you've discovered that you're taking a long time, would you like to have then a better, more scalable algorithm?
There are people working on it, for sure. But I'm not expecting any breakthroughs the next 5 to 10 years, which is sort of the time frame we're trying to do something important in. But like David, I know there's somebody working on scalable.
That's definitely interesting. It's a hard problem.
Right. Yeah. Is this the one that Lin Wang is working on?
Well, in a very general sense, but it's a different code.
Okay.
And the other technology that we'd really like to bring to bear here is checkpoint restart. So another way to tolerate long times is if you can quiesce and then restart from where you ended up. And that's a technology that actually, unfortunately, was in better shape 10 years ago than it is now. The old Cray vector machines were very good at that. And we're trying to resuscitate that technology.
That would be really, really good, because when you restart jobs, DFT jobs, typically you lose a ton of time. It's just like it takes forever and it's not very efficient. So doing that from a more core level would be great. So what we do, one of the, this is the things to get around it. If you can actually do what you want to do with good performance, then that's fine, right? If you can't, you have to work within the system. You have to consolidate your jobs maybe into one script, if that works within the queuing policies. That's kind of the tasks, you put it into one task which has multiple materials and so on. I love this graph. This one David also showed to me. Apparently it's very, very well known, and I can say it really captures how my team has the sentiments of my team. So we got tons of CPU, millions of CPU hours, right? And we were going to go to town with this and calculate the whole known world of materials. We were very excited. And then, of course, it didn't quite work because it was 2 weeks of blocks, and we could only submit so many things, and we have to work around that. And people like David is trying very hard to get the most out of our codes and our computations and our scripts. But there still was like very much this sort of value, like, oh my God, we're never going to be able to do this. And then we're working our way up to the steady state of happiness. Not as high as the excitement, though. And this is a good slide because it kind of shows that my team puts a lot of effort now into managing this workflow. Managing jobs, finding out where they failed, why they didn't finish, maximizing the throughput what you got, right? If you got 8 days on 500 nodes, you want to make sure that you put as much, that block of computations you put in, you want that to be optimized for that time and those number of nodes, right? So there's a lot of scripting and workflow management going on, and you have to be sure that you don't put too much time into that for your system. You have to look at the system, see, can I work with this? So analyze the whole problem from the beginning.
So the next to last box is UQ is uncertainty quantification, and V is validation and verification.
Yep.
Could you say just a little bit more about how you actually decide to trust the data? I mean,
yes. You know what? That might fit better in the next. Yes.
Okay, fine.
I'll get back to that. And I forget your question. Remind me.
I will remind you.
But I'd just like to point out that this is a very holistic problem. You have to analyze how much effort you're going to put into that workflow. So right now, my people have been working for, 3-4 months on a new workflow architecture to make sure that they get the most out of this, out of NERSC, and making sure that they can automatically submit jobs, get them back, analyze them, put them back into the queue if that's needed, or put them in a database and analyze them and put them to the materials property. So it's a whole big system. There are different ways of making the most out of what you've got in terms of computing. Charge factors, if you can wait a bit longer, you maybe get something cheaper. If you can wait 1 week or 2 weeks or 3 weeks, you actually may get cheaper computing time. Scavenger queues, transfer queues, that's not something that we do much. The transfer is basically if you need a lot of cores up front, but you can do with fewer in the end. That's something that's sometimes permitted. But you have to think about the run limit, the queue limit, and the wall limit. And those are painful parameters that if you don't own your own clusters, you have to live with. Okay, so assuming you get you deal with all this pain. And I'm not dealing with it personally. I just have to deal with their grievance when they come and complain to me, my people. But assuming you do that, does this work? I mean, I gave you the promise in the beginning. Material science would be really cool if we can solve all these problems. Let's use computation. So I'm going to show you a few examples, which I hope to show you that it really does work. But I'll let you judge. So in 2004, Duracell, that makes the little AA batteries, that is owned by Gillette, the razor blade company, that is owned by Procter & Gamble, which basically owns everything, I think, except for Nestle, came to me and my colleague at MIT and asked us if we could come up with a better cathode for alkaline batteries. So currently they were using manganese dioxide. So that's the manganese dioxide there, and they had zinc anode, and they put this in an alkaline KOH electrolyte. It's basically a stick in a can. It's a very simple technology. It's dirt cheap, literally. You dig manganese dioxide out of dirt. It's, if you ask Duracell how much it costs to make one of these cells, they don't dare to tell you because they make so much money out of them by selling them to you. They throw a nickel on the table. The next time you go to the store and buy one of these, you think about how much you pay for it. Anyway, but they were scared because they'd making a lot of money out of these batteries for a long time, and they wanted to know, is there anything better out there that our competitors might come up with and that would screw us, right? Because we'd really like to keep on selling these batteries. So they asked us, can you come up with something that has higher energy density than manganese dioxide? It's an old technology. And me and my colleague, we have never done like a high throughput discovery project before, but we had gotten enough confidence in our methods by 2004, knowing that we've been calculating properties of battery materials one at a time for a long time. We know how to do this. Why can't we do it for 100,000 materials? Should be doable if we get the computational power to scale it up. So Procter & Gamble gave us their giant computer cluster and $1 million and a year to do it. And we turned all of their specs. Basically, we sat down with their experimental team and we found out what they want, and we turned that into computables, and that's the stuff over here, right? Where you have a phase diagram, you have a conversion from one high material up here going down to a lower energy density. You get a voltage curve associated with that. We also had to be able to predict stability in very, very alkaline water. It's not really water anymore, so viscous is almost like a gel, right? If you have 9 molar KOH, I don't know if, hopefully you've never been close to that. It's extremely corrosive. You put anything into it, basically. But manganese dioxide survives. And this is, again, those Probet diagrams. And actually, we were able to, using experimental aqueous ions and our calculated solids. And that was very important, right? Because we want to be able to predict properties of solids that no one has ever seen. But we want to be able to predict whether they dissolve. So we have to combine those two sets of data. And doing that, we were actually able to predict dissolution in aqueous. So this is the experimental and our calculated Probet diagrams. And as you can see, the corrosion regimes, which are the aqueous ions here and here and here and here, are quite well reproduced. So we could predict whether materials are solid materials that were completely new and no one had seen. That's one of the things we had to be able to do to make this project work. And the screening strategy was taking all the inorganic compounds in the world, which is, depending on which database you go to, between 30 to 50,000. It's on that order of magnitude. So it's not an intractable problem. It's not like the protein world or DNA sequences or something like that. It's much easier. But we can permute them. So we can take the crystal structures and we can look at the different cations in them, and we can substitute other elements and that way generate new materials, new starting points, new candidates. So in the order of like we looked at about 100 to 200,000 materials. And we calculated first a few of them, and by few I mean a few thousand. We data mined that result for the things we wanted, voltage, capacity, stability. And then we fed that back into the loop. We generated new compounds that would be better guesses and better fits. We screened those. And in the end, I think we computed about 10,000 to 20,000 by first principles. And the first batch was not a good guess. The second batch was slightly better. And by data mining the results, we could get better and better suggestions for new materials that would fit our criteria. This is one of those cool data mining plots that we got. This is actually the y-axis and the x-axis are the same. It's the elements. And the green dots tell you whether you have a high formation energy or not. So basically, which elements like each other. And this is typically in oxides. So it's actually you're not supposed to be able to read these two because this was a consulting project and they don't really want to give out this data. Some of it I will tell you because they've patented it, but not all of it. So here, let's say you have something here. Let's say you have lithium together with manganese 6+, and that may have a green dot because they really like each other in oxide environments. So one of the things we found out by this data mining was how to stabilize those high valent cations that you need for high energy density. You need things like nickel 4+, cobalt 4+, manganese 6+ to be able to take up a lot of electrons. And that's the way you get energy density, right? But it's hard to stabilize them. They don't like to be that highly oxidized, so we'd like to know which elements that they really like and feel comfortable and fuzzy with so that they stay in that compound and they don't dissolve and go into like decomposition products. Another data mining exercise that we had to go through was understanding dissolution. Which elements resist alkaline media the most? And as you can see, everything here is basically blue. Everything dissolves at pH 15, most things. But there are some white regions, and those white regions tell you which elements are more likely to be stable in alkaline media. And you put a little bit of those in the compound, and suddenly you have something that is more stable and that can resist the dissolution better. So putting these data mining things together, we were actually able to design new compounds that had the best kind of properties that you were interested in for this particular application. Long story short, we screened 130,000 compounds by these data mining techniques and first principles. About 1,500 were a lot better by energy density than than manganese dioxide. 200 fit the criteria when you went down to demanding that they had to be stable in air and the electrolyte, and all their decomposition products had to be stable too. Let's say you discharge your battery halfway and then you put it in your wardrobe for a while. You take it out. You'd like to get the last thing out of it. So the decomposition product had to be stable too, which that's requiring a lot. This is a plot showing that where these compounds lied. And a few months ago, I couldn't even say what they were, but now I can at least talk about a few of them because they've been patented. One of these patents is very new. That's the nickel 4+. If you go into this patent, you'll see all these rules that I talked about. How to stabilize nickel 4+ in very alkaline environment, which kind of elements they'd like to put in there. And they haven't made all of them. They've made some. But if you've ever seen a patent, I hope you haven't. They're unbelievably boring. They list everything that you could possibly think about. And they say things like may be good and could be good under a certain scenario. They like to cover as much as possible. So we gave Duracell all these 200 compounds. They're still working on them. They're still patenting them. And one of the things that made this was a funny thing, because obviously the first thing that Duracell did when they came to us, they excluded certain elements. They didn't want gold in their batteries. Not platinum either. So we didn't even try on those. But we tried things that were moderately inexpensive, like bismuth. Bismuth turned out to be a great material. It was a high valent cation, and it actually resists dissolution in pH 15 as well. When this got to the lawyers in Duracell, they sat down and looked at the world production of bismuth. And they got very unhappy when they saw that, first of all, it's very small, and second of all, we don't have it domestically. It's, of course, all in China again. So we don't want, and again, you're going to supply a whole market of AA batteries. You don't want to be buying that from China. So they told us, no, you can patent it, but we don't really want to try to really commercialize this for this reason. But what they're very happy about is that they have the patent. And this is, again, I don't know, how many of you guys recognize this? You do, right? Yeah. And David, okay, this is an 80s movie test. It's the last picture out of the first Indiana Jones movie, where they basically wheel the Ark into this giant warehouse, and you never see it again. Yes. So that's a bit how we felt when Duracell took all of these great materials, and they're not going to use them. They're only going to patent them and make sure that nobody else uses them. So we weren't very happy about that, because we really wanted to see these new materials on the market, feel a bit of pride in our ability to predict new materials. Yes? They last, I think, about 15 years, something like that. So they have about 15 years to commercialize them. Bismuth now was, the bismuth one came out 2 years ago. The nickel one came out this fall. They have a bit of time, but let's hope one of the competitors start to do this, because that's the only thing that's going to get Duracell moving. But it's probably going to turn into lawsuits. So the only one that's going to be making money out of this is the lawyers. Anyway, I'm very cynical, but
so the computer business is sort of famous for large purchases of patents to protect one another. Does that happen in the materials industry too?
So we have some famous lawsuits in the lithium-ion battery world, which are still ongoing. And yes, they've been multi-million-dollar patent suits, which is ridiculous, because, yeah. Not going to get into that. I'm just going to get upset. Anyway, so we knew this worked, at least. We were happy about that. So we went back to MIT, and I came to LBNL in 2008, so I was still at MIT when we started this, and decided we're now going to do it for lithium-ion battery cathodes, because they need to be higher energy density, like we talked about the DeLorean in the beginning. Not a reactor, but we need we need better cathodes. And we were going to do it at a university where we have some influence over how these materials get made. And if somebody wants to license them, that would be great. It was actually still sponsored by 2 companies. DOE still hadn't gotten wind that this was a good idea, or the government. But companies, they love this stuff because they love to patent and protect their things. So we did this MIT, again, screening criteria. We look at a lot of different things that are interesting for lithium-ion batteries, structural stability, voltage, oxygen release for safety, lithium mobility. You want to be able to have high rate and to discharge and charge your battery. So all these things we can compute. And between 2008 and 2009, and I left in the middle there, the team at MIT screened about 20,000 materials for cathode applications for lithium-ion batteries. And this is a plot just meant to impress you, but it's going to tell you also that this is the real advantage of doing a multi-property optimization, in the sense that you have voltage versus capacity. These are just two of the metrics. And again, these are the kind of metrics that a person in the lab would be able to look at. But if you have more properties than that, you know that high voltage destroys the electrolyte. You're not going to go there. And we can calculate that oxygen release from those cathodes. High capacity tends to be associated with instability. If you draw too many lithium ions and in out of a structure, it's going to collapse. They're just going to be happy about that. And that we can get from our phase diagrams. So again, we have a lot of more properties than these available, and that's how we design. We look at all of them, not just a few. These are two of the...
Question there. So these are all potential materials.
Yes, we have computed all of these. These are all plot.
And how many real materials are there in that little ellipse? I mean,
real in the sense that they have been seen?
Or tried in a lab, yes.
Yeah, tried in a lab, that is currently the bottleneck. I think we have maybe tried of the order of 50 to 100, maybe by now. And that includes all the different sort of compositional degrees of one material and different synthesis methods. But
And they're all in that ellipse. I mean, you didn't try building ones that were
that
in
was
some
on
other...
the outskirts.
Yes.
No, we're quite confident in our ability to predict the properties, and we know we shouldn't go out of there. So these are two of the success stories. These are two completely new materials that have been predicted by our first principles methods, and we've made them. They work. They have not been seen in Mother Nature before. And from Mother Nature's perspective, they're metastable. This particular one here, I really like. These are the carbonophosphates. And when you show this formula to a lithium-ion battery cathode experimentalist, he goes, no way. He has never seen anything like this before, and he would never have thought about it, and that's the important thing. This is what computations bring to the experimental field, right? It brings them out of their comfort zone. They're used to layered oxides, and they can beat the crap out of those. They do all different kinds of versions of them. But they never think about things like this because they wouldn't. This has never been seen before. The really cool thing about this guy is that it doesn't release oxygen when you heat it up. It releases CO2. That's the fire extinguisher. So it's actually its own built-in fire extinguisher. Anyway, so these are really cool. So it worked for two projects. Whether these things are going to be actually seen in cars, the story is we don't know that yet. These are pretty new results. They were published last year. But what we would like to do is do this for more than just the things that we can predict. So I'm mostly based in the battery space, but there's so many other fields that need this kind of computational engine and property calculations. So that's why we started something called the Materials Project, which is a free online resource. And this is what my people at LBNL mostly are working on, to bring all those computations out in a way that it can be freely accessible for experimentalists in any field, so that they can search for materials that are useful for them. So they can answer questions like, what are the properties of known materials? Oops. What new useful materials might exist? We have a structure predictor that is online that data mines the known world of materials and gives you suggestions of new ones in a particular chemistry if you submit a search like that. And how can I optimize a material over multiple criteria? So we're hoping to bring information to people like that who ask those kind of questions. This is a collaboration. We started MIT and LBNL, but we actually have a lot more partners now. We have two sort of founding institutions, but a lot of partner institutions that are bringing either people or algorithms or data to the repository. And yeah, I think I've said most of these things, filling in missing property data. So just to give you an idea, how many elastic constants do you think are measured in the world? If there are 30,000 known inorganic materials, how many of those do you think have been measured for elastic constants? Basically how a material responds and if you tug and compress it. Order of 100. 100, 200? It's mundane, boring work. Who wants to do that, right? But computationally, we can do that very quickly and very reliably. So that's and we can go after it very fast. I'll give you some examples. Same thing with band gaps. Band gaps, very important for photovoltaics. Again, order of hundreds are known, not more than that. Very boring research. Nobody wants to do it anymore. And who wants to fill out a table somewhere in some book, right? That's not exciting science. So missing property data is huge because that gives you a lot more to choose from. Assist researchers in predicting new materials. That's the structure predictor that I'm going to talk a little bit more later. And interactive analysis, tools and codes. So we actually have some tools for computing people like me. If you want to manipulate a structure, you want to substitute things into it, we have automated tools online that can do that. Enable rapid screening and data mining towards something that we, of course, would like to call the materials genome. This is, yes?
Question?
So materials, like if you put I got a talk yesterday on trying to liquefy aluminum, and then what they do is they put silicon in to somehow make it a little bit easier.
Yeah, so they're going to liquefy aluminum and they put silicon to make that easier to lower the melting point?
Must be.
Yeah.
And so then when they put it in, they're looking at stretching or elasticity. Mm-hmm. So could you just, and so what they see is breaking, like they find that it's more brittle.
Yep.
And can you quantify that? Are you able to see that with your computational models?
So brittleness, so if it's breaking in the sense that you're actually, so when you tug on the material, first it's elastic deformation, right, and it's still holding together, but eventually you go into the plastic regime where things are not linear anymore and eventually it breaks. That actual breaking point is very hard to predict. What we can calculate is something called ideal strength within the elastic regime, which is sort of the end of that elastic regime. That is doable. The plastic regime, you would have to go to more approximate, continuum models that uses our kind of information as input. So I wouldn't say I can calculate it directly, no.
I see.
I can give you an estimate based on the elastic regime, but I can't really exactly pinpoint it. It's you would have to use other kinds of methods coupled with ours.
You can look at aluminum and you can also look at silicon.
Yes, and I can look at the compound together and see if that's different from the two endpoints, yes.
Oh.
Yeah, so trends would probably be very, very doable. So this is the computational that I talked about a little bit about before, the automation engine. We actually have a database in the center that actually both stores the data from the computations as well as manages a queue. We have a database that imports and spits out the new calculations and keeps track of them all. And the people who have designed this, they have made sure that we input data, we run it, we output it, we analyze it, then we put it into a web interface. And it's all connected. Very cleverly done, and they all have a huge amount of headache, the people who work for me. But they're very smart, and it's quite the thing to be part of this. And I want to acknowledge all the people who have helped me build this, which is the NERSC people, the MIT people, CRD people, and us at EETD. So we have a number of different apps. We try to be a bit cool that way. We have apps on our web interface. They are this phase diagram app where you can put in any element and you can get a phase diagram out of it. We have the lithium battery explorer where you can explore different intercalation as well as conversion materials in two different ways. The conversion route was the one I showed you with the alkaline. That's basically when you decompose the material. Intercalation is where the material basically stays the same and you move the ions in and out. Two different ways of getting energy density out of material. The structure predictor, the materials explorer, which is sort of general materials properties, the crystal toolkit for computational people, and the reaction calculator if you just want to know how much energy can I get out of hydrogen plus oxygen giving water, the fuel cell thing, or anything else for that matter. Just to give you an idea of kind of like the stuff you can get out, if you all put all this data into one repository and you analyze it, instead of those 200 elastic constants or the 300 band gaps that we know in the world, we already access phase diagrams for 28,000 systems, 35 reaction energies. And again, reaction energies, if you have to go to Kubachevsky or some book like that and get the Gibbs formation energies for materials and combine them, again, order of a few hundreds. By computing, we can access orders of magnitude more than that, relatively easily. Some properties are harder, like the plastic stuff, very hard. Some properties are very easy for us, and we should make the most out of that. The easy one should come first. The structure predictor is really cool. This is one, again, those data mining maps. So we try to look at which elements like different crystal structures. How do they like to combine in those crystal structures? We've data mined the whole known world and our computed data. And if you go to our website and you submit a structure predictor structure predictor request, in about a few hours, because this is actually done on the fly for you privately, you get a list back of suggested compounds in that category. And if you're an experimentalist, one of my battery people that works with me who's an experimentalist, he loves this app. He goes to it all the time and try to come up with new materials that way.
So the word privately is interesting. So you don't keep a database of all the old calculations you've done and just grow your information over time?
So the whole database of computed properties is just controlled by us, and it's available for everybody. But a structured predictor request is actually not a calculation itself. It's not a first principles calculation. It's a prediction based on calculations. And unless you, as a user, make it public, it's not public. It's stored for you. It's a permalink in that sense. It's stored for you, and you can go back anytime and look at it. But nobody else can look at it unless you want to send it to somebody. So it's a different kind of hierarchy. Does that make sense? The computations themselves.
I understand. I was just wondering if there's some data mining on all of these that could be done that would make sense.
Yeah, I'm a little worried about doing that because a lot of people have problems with privacy of this. Okay. We actually have we went through quite a bit of a exercise in writing a privacy policy for this, because there are a lot of companies, as you'll see.
Well, just become molecular Facebook, and then you can do it. Yes.
Yeah. There you go. I'll build Google and sell it all to the government, right? This is one of the cooler things. If we're talking to electric car battery companies, they're very interested in the safety issue for good reason, right? They'd like the left-hand picture is a good one, pretty girl and car. Right-hand picture, not so good. So what we have, for example, this is again from our website, our calculated materials. We have the voltage curve for them, and we also have the oxygen evolution curve. And these oxygen evolution curves as a function of temperature. Nickel phosphate is actually a compound that some people in the world are still working on. They hope, because it's a very high energy density material. It would be great if it worked. It releases oxygen at room temperature. It's a bomb. There's no way they can possibly make this work, and they should know this, but they're still working on it. The second one is the one that we predicted, the carbanophosphate, is better. The safest one that is commercially available is lithium iron phosphate. It requires quite a bit of temperature boost before it starts releasing oxygen. And this is just one of the issues. This is just thermodynamic release of oxygen. But it's at least a proxy to safety. You should not be working on a material that's thermodynamically driven to release oxygen. There's no way you're going to contain that in the long run. So this gives you an idea of how you can use that kind of data. We've been up since 2011, October. So not that long. We have 2,000 registered users, a little bit more. It grows every day. I get quite the kick out of looking at the registered list. Please go online and register, even if you don't use it. So far, we've had about 6,000 phase diagrams generated by users, so they clearly like this. 7,000 structure predictions executed. Clearly, a lot of people understand that this is a driver to making new materials, because it's really hard to come up with new structures yourself. A lot of these experimentalists, they know exactly which kind of chemistry they would like a new structure in, but they have gone through their known comfort zone of 20 crystal structures. Here they can get new information and new sort of inspiration to making new compounds. And these are our current partner institutions. Down there, Mark Asta, and here you see in the Material Science Division, yes.
Do you have a breakdown by country?
We haven't done that, but there is a fair amount of Chinese. I've seen. And Koreans. Samsung is very happy. We occasionally get a little feedback email saying, I cannot get through, I cannot log in because of the firewall. It's like, yes, I'm sorry, sir. It's not our problem. So the idea is really, the sort of vision here is that LBNL and MIT and our partner institutions, we're the sort of developers. We're going to feed all this information about different materials properties to the single investigator that comes up with new materials, and that's going to bring science solutions to the world. And we're not going to do this, just for ourselves. We already know that it works. We did it for cathodes. We did it, for different kinds of chemistries. But we want to bring this to other groups as well. So this is just a long list of all the things that we could do, that we think we could be doing. We've done it for alkalines and lithium ion. I'm doing it for rechargeable magnesium ions. I'm actually a co-founder of a small startup company. So we're using the same idea of computationally finding new materials for magnesium batteries. And we would like to go after things like sodium-ion electrolytes, solid-state electrolytes with really good diffusivity. It's a perfect computational problem because we're very good at finding these paths of high diffusion in materials and screen them for that. Mercury capture from gas streams is a huge problem in China for coal liquefaction, that's the word, right? Corrosion stability in water, we're soon going to bring all these Probay maps online as well. We have them for all the elements, and once you have them for the elements, you can tie all the computed solids that we have and predict whether they're going to corrode in water or different kinds of acid and alkaline conditions, which is huge for people who try to design materials in these very corrosive environments. Photocatalyst is one application of that. I just heard Pei-Dong Yang talk a few weeks ago about his photocatalysts. And on one slide he had, well, I have pH 1. And he didn't say anything more about that. And I asked him afterwards, how are you going to stabilize things at pH 1? I mean, most things actually just completely fall apart. And he said, yes, that is a problem. I'm going to put stuff on the surface that protects my catalyst. Stuff on the surface. So he has something that first has to get the sun rays, and so that has to penetrate that layer, right? That's first, that layer has to be completely, that can't screw up his material, and it has to protect under pH 1. So that's the kind of thing that I'm talking about, that most of the experimentalists who work in these fields, they concentrate on a few properties, but they don't like to talk about the other ones. And I'm not saying anything bad about Pei-Dong Yang. This is very common to everybody. Everybody who works in a field, they concentrate on a few properties, and they don't like to think about the rest of them. But hopefully, maybe he can use this app when it comes up. Thermoelectrics, really cool materials problem. If you can find a material that converts heat to electricity, oh my God. I mean, think, cars that have really warm, components everywhere. You put a little bit of these materials, and suddenly you can power all the stuff that goes on electrically in your car, just from that waste heat. A lot of waste heat going on in industry. But unfortunately, the materials that we know today that have this functionality, they're not efficient enough to motivate high-scale commercialization. Surface energies and nanoparticles. Anyway, so all these cool materials problems, we hope to be able to help with this computational effort and to become, and I know Google has a bad name these days, but anyway, to become sort of like where you can just enter things, and we actually have, I think as of Monday, we're launching Moogle, right? Out of our there's a little search bar that we call Moogle for Materials Google. Anyway, we're trying to be fun.
I hope you don't get sued.
Yeah, we have thought about that. We will take it down if they go after us, but I don't think we're big enough yet. So our website is materialsproject.org, and since I almost never get to put the president on my slide, I just had to do it. Actually, I said before that mostly companies think that this is cool, but last year the government caught wind that this is really cool. So they launched something called the Materials Genome Initiative. And we were actually, that was our name. We were materialsgenome.com or .org for a long time. And then they came to us and asked us, can you please give it up? We need the name. And what do you say when the government knocks on your door and say, can you give me your name? You say, yes, of course, Men in Black, right? What do you? So yes, we gave up the name and became the Materials Genome Project. And they launched the Materials Genome Initiative, which aims to fund computational tools, software, and new methods for materials characterization and development and acceleration of new materials discovery. So it's really sort of exactly down our alley. And our effort, this materials project, was also, when we launched, we were recognized as the first of its kind search engine which will speed materials research. It's a little bit of recognition for our work. And I'm a little early, but if you have questions, I'll be very happy. More questions? Yes?
Right. Let's thank the speaker.
So when you said one material, one machine, is that something that could benefit from distributed computing, like SETI and folding at home?
So SETI, you have to explain these things to me. SETI and study at home. Yeah, that might not be a bad. So if we can sort of launch people's own computers, that's what you mean. Yeah, no, that might be a way of doing it. We'd have to be able to control how they're doing it. So we have to generate the input files for them. But if they can run VASP, the problem is that some of these codes they cost money, and so we can't. Yeah, VASP costs $7,000 per license. So not everyone wants to do that. There are freely available codes, though. So if we go to that, it's quite a bit of hassle to compile it on your own machine. So it would be a quite dedicated user, I would say, or person out there. I remember when one of my boyfriends in the early 90s, he ran he tried to find prime numbers on our computer at home, which made me really upset because I wanted to play computer games. But, but he was dead set to find the next prime number. That's perfect, right? Because you can do that on any machine. You don't have to compile a lot of stuff, But this takes a little bit more effort. So in that sense, it's harder. I don't know if, David, if you have another perspective on this.
No, that you have to have really dedicated users. At $7,000 a license, you really have to have dedicated volunteers. But yeah. I wanted to speak a little bit to your question, Jim, about accuracy, right? And
right.
very broadly speaking, the computational science community could do a lot better when it comes to showing that it got the right answer for the right reason and that sort of stuff. Probably the worst offenders are people who do one gigantic simulation and they conserve energy or whatever, and then they believe that they have a accurate representation of what they're simulating. In this case, it's actually a really wonderful opportunity to do a kind of layered intercomparison between methods, because approximate methods are great, as long as you understand the limits of the approximation and where it applies and where it doesn't. And the systematic nature of this type of high throughput computing gives you lots of data points to figure out where those things are. So imagine that you do at least two levels of approximation in the chemical theory behind it. Then you can develop a map that shows where one method works and maybe where another one doesn't. And then the same applies to the software space, is that a lot of people in chemistry, in particular material science too, kind of grow up using a certain code, and then they just stick with that, and they think that that's the only way to do it. And then whole communities kind of form around that mentality. And so, doing multiple methods, multiple codes on the same system systematically is a way to kind of show, in direct ways where codes have benefits and don't. And for DOE, the people at LBL have developed some very specialized high-quality codes for certain types of physical systems that a lot of their authors regret that they've not seen wider adoption, in other places. And so this is, I think, one way to kind of catalyze that by saying, well, if you want to get really high-quality answers for lanthanide or actinide materials, right, maybe this DOE code is the thing that you should be using.
I should also say that whenever experimental data is available and we've been able to import it, we do compare. So for example, if we compute a material, we have all of the ICSD imported, which I'm not sure the ICSD likes, but we don't publish it online, but we have that data because we bought a license for it. So what we've done is we've data mined bond lengths and volumes per different elements, and if our calculations come out with a very different, that's outside of the sort of the normal curve of that, we flag it as a suspicious entry. And that's one automated way of checking whether the calculation went completely haywire or whether it's a reasonable result. Yes?
On that topic, it seems like you're collaborating with MIT.
Yeah.
So are they not adopting it as well? It seems like you have kind of both coasts.
Oh, you mean we have two databases, or two? What do you mean? And two?
You were saying that not enough people had adopted the LBNL code.
That's probably what David said.
Yeah.
Oh, okay.
The MIT and LBL folks are, in very fluid, collaboration with one another. The Department of Energy, has developed a lot of different software that hasn't really made it very far out, and that's kind of a.
So some people at LBNL, have spent a fair amount of years. I think one of the codes is Lin Wang's code, which is very good at looking at bigger systems, so large nanoparticles. I think he freezes part of it and then he treats the other part of it, because obviously when you have more atoms and electrons, again, huge computational costs. So I think one of the things that his program does is that he freezes part of it and he treats the other part well, depending on if you're interested in the surface or whatever. And that's a really neat code, but unless you've been in his group, or you have some other exposure to it, you wouldn't be using that code. You wouldn't even know it existed. So having a sort of vehicle for testing, systematically testing and advertising codes that don't cost money are just freely available is a great resource. But that doesn't exist.
I'm reminded a little bit of the situation in electronic structure going back many decades that John Popel, who's sort of the father of electronic structure theory, he was the first one who sat down and said, the basis sets that we're choosing are important, but we shouldn't just choose them based on who your postdoc, who your advisor was or something like that. And so they began to set up some benchmark problems that all the basis sets that people were choosing were, tested to 9 decimal places, to see really, which ones are accurate where and that sort of thing. So it's only by systematics that you can develop a kind of rigorous understanding that way.
So can you go into a little more detail as to why for each compound or element that the computation is not scalable? I guess I didn't quite understand.
So scalable in the sense that if I spit it out on 100 nodes versus 50 or 30, it actually
that there's a limited number of cores that you can compute one material on.
So my understanding of this, and this comes from when I was a grad student, right, and I wrote my own parallelization of these codes, was that it had to do with communication, that you have to take all the information from all the different cores that you're using and put it on one and then spit it out again. And you have to do that so many times that that becomes the limiting factor.
Another commonly... sorry. Another commonly given response is that chemists don't write very good software. So,
That might be true.
So should we interpret this as an opportunity and maybe an invitation for a summer internship to work on one of these things?
If any one of you guys are interested in this, we would love to have you work with us. It's been extremely productive to work with David's team, who are computer scientists, and this is very much a multidisciplinary effort in the sense that we're using knowledge of material science and codes on computing clusters and making that into the most efficient vehicle forward. So, yes, absolutely.
Okay, or perhaps a class project for the next CS267 if
yep.
nobody signs up this summer.
Yep.
Okay.
Are there any chemists or materials people in the room? Yeah.
So you have a summer job.
If you want to. It's a very nice team to work with, I gotta say. My people are very nice.
So is, I guess, the variety of the codes and sort of the difficulty in getting these things up and running on new computing platforms, have these been tried on more of a cloud, MapReduce, Monte Carlo type elastic resource?
So Google actually offered us a year ago, was it 1.5, 2 years ago, to be using their spare computing power, which is 1 CPU hour model, right? And it doesn't work because we don't, like I said, if we have one node that doesn't communicate with anything else, 8 cores or whatever, and you have 1 hour of that, most of our jobs won't finish. So we will have to then spit them out, get whatever crap we come back, like half finished, third finished, whatever jobs, take them back home, put them back out again with all that data and keep it intact, and do that over and over again until things that take 2 weeks that relax on 1 hour basis, it's going to be horrible. And we talked to them a bit about it and asked them, are you flexible at all? Can we get more than just 1 CPU hour? Or what's the kind of data storage? Can we store our data and then get it back up again when you can give us more time? No. Nope. Just 1 CPU hour.
Is it possible to do sort of a culling of your herd of computations using that method? You submit all of your jobs to that format, and if it finishes in an hour, great, you have the result. If not, then you've removed all of or you've removed a certain set of short guys, and you submit everyone else to Hopper or whatever.
That's possible, but the benefit of that is that there's not that many compounds, honestly, that finishes in 1 hour. So we'd rather just do them. I mean, I can do that we can do that on Laurentium or whatever, and it is a small amount. What takes time are these longer ones, and that's what we have to put. Those are the ones that cost us the most effort too. That's what we really need a better solution for. So the checkpoint restart is a great solution to that, because that's one way that we could actually utilize anything, not just Hopper, whatever is out there, better. The small jobs are not an issue. They can basically run everywhere. So yeah, if my world was filled with small jobs, I would love it, but it isn't. Sad to say.
Okay, well, thank you, speaker.
Thank you so much.
And let me just for the poster session. The plan is next Thursday that everybody will step up here and give a 1-minute summary of your posters, and we'll video record it. And then we'll step out into the hallway and we'll have easels. We'll bring those. We also have poster board if you don't have your own poster board. and then we'll walk around and talk about it. So, and at some point in there, I will step out and you will fill out the student evaluations that are done every semester as well. So as regarding posters, we have printers in the Par Lab if you don't have printers, and we can just communicate about that as necessary. Okay. Looking forward to your posters.